In this video, we're going to take a look at what happens when we try to do curve sketching with fractional exponents with the denominator being odd. And the first thing we're going to do is investigate these on our graphing calculator. So if we pull up our graphing calculator and we go to y equals, and let's go ahead and type in x to the 1/5. So we find the xt theta key. We're going to need our exponent, so that would be under the clear button. And we're going to do 1 divided by 5. Now, if you have a old school calculator, then you might need to put that fraction inside of parentheses. Now, if we go ahead and press graph, and I'm going to go zoom 6 so that we get the standard graph. You'll notice that x to the 1/5 looks like that. We refer to that as an S shape. So our x to the 1/5 is going to be a kind of flattened out S, and I want you to notice that as we go through the origin, we have a tangent line that's vertical. So we're going to have a point of non-differentiability there. Now let's observe what happens to the graph if the numerator becomes even. So I'm going to go back to x is 1/5, and I'm going to arrow over. I'm going to change that 1 into a 2. Well, now if I graph, we get this sort of V shape, which I'm going to refer to as a birdie. So when we have an even numerator and an odd denominator, we're going to come down, it's going to curve, and then it's going to bounce back up. Now, you'll notice at the origin what we have there is a cusp. A cusp is a point of non-differentiability. Just like over here in example 1 where we have this vertical slope, which is also a point of non-differentiability. Well, let's see if this pattern holds true in example 3. Now, again, we have an odd numerator and an even denominator. So if I go back to y equals and I change that 2 into a 3, if the pattern holds, we should see an S. Well, so if we hit graph, notice that we do get an S. Only this time the S is a little bit steeper. Now, if we continue that pattern, we would continue to notice that those things occur. So the rule for this is that if we have an odd numerator and an odd denominator, we're going to get some form of S. If we have an even numerator and an odd denominator, then we're going to get some form of birdie. Well, now let's take a look at this exact same thing, only using some calculus. So I'm going to go ahead and erase this work, and let's go ahead and prove this a little bit. So let's start off with example 1, and we're going to go ahead and do the first derivative to find increasing, decreasing. Well, so the derivative would be 1/5 x to the negative 4/5, which could be written as f prime of x is equal to 1 over 5x to the 4/5. Well, so when we go to set that equal to 0 to do our increasing, decreasing, notice because the numerator is a 1, this thing is never going to be 0. But we have to look at domain restrictions. The bottom can't be 0, otherwise we have an undefined situation. And one of the things we need to know algebraically is that when you have a 0 to any power, you're going to have a problem there. So we have a problem at x is 0. So we're going to have to do a sign test and see what's going on. So we have a point of non-differentiability at x is 0. X is 0, point of non-differentiability, because it creates an undefined situation. If I pick something to the left of 0, like -1, and I throw this in, Well, now what we need to realize is what happens when we do negative 1 to the 4/5. Well, because the numerator is even, we have an even number of negatives, so that's going to be a positive, but 1 to any exponent is still 1. So that's going to make this just positive 1. So we have a 1/5 times a 1, so that's going to be a positive. So this graph is going to increase to the left of 0. If we pick something to the right, like positive 1, same thing. We're going to get a positive, and the graph is going to always increase. So if we have a graph that's always increasing, but has a point of non-differentiability at the origin, then we're going to get an S shape. Now we could further check that by doing the second derivative. If we did the second derivative, we would learn that we're concave up to the left of 0 and concave down to the right of 0. So let's go ahead and take a look at that just to verify that that's what's going on. So if I take my second derivative and I'm going to look back up at this step, I'm going to get as my second derivative negative 4 over 25 x to the negative 9/5. Now that can be rewritten as f double prime of x is equal to negative 4 over 25 x to the 9/5. Well, when we set that equal to 0, we still can't get a 0 because negative 4 on top can never be 0, but we're still undefined at 0. So if we go ahead and do a sign test again, when we pick to the left of 0, like negative 1, and if we plug in a negative here for x, we have a negative on the top, we have a negative on the bottom, double negative is a positive, concave up. So if we have increasing concave up, that's going to give us this shape. If we pick to the right of 0, which is 1, we get a negative on top, a positive on the bottom, so negative concave down. So we have increasing to the right of 0, concave down, increasing concave down, verifies our S shape. Let's go ahead and do one birdie in the same way. So let's just do example 2, and we'll kind of ignore example 3. So again, we're going to do our first derivative, which would be 2/5 x to the negative 3/5. Could be thought of as 2 over 5x to the 3/5. Again, when we set that equal to 0, we have a problem at 0. So if we choose something to the left, like negative 1, now this time, when we plug in negative 1, we have an odd numerator. So that's going to create a negative value. So if I have a positive on top and a negative on the bottom, I get a negative. So the graph's going to be decreasing over that interval. If I choose something to the right of 0, like positive 1, now I've got a positive number divided by a positive number is a positive number. I know the graph increases to the right of 0, but has a point of non-differentiability at 0. Well, that's making me think now that my graph is going to be this birdie shape, because it decreases, then it increases, and has a point of non-differentiability. If I want to verify the concavity, second derivative, so that would be negative 6 over 25 x to the negative 8/5, which can be rewritten as negative 6 over 25 x to the 8/5. Now when I set that equal to 0, I can't equal it to 0 because the numerator has a constant value. I do have a problem still at 0. So when I do my sign test, if I choose something to the left of 0 like negative 1, now when I plug in my negative 1 here, since the numerator's even, I have 8 negatives which make a positive. Top's a negative, bottom's a positive, we get a negative, so we're going to be concave down. If If I pick something to the right of 0, like 1, and I plug that into x, I have a negative divided by a positive is a negative, and so we're still concave down. So to the left of 0, I'm decreasing concave down, gives me this shape up here, and then I'm increasing concave down, gives me this shape to the right, confirming my birdie.